Hello, in this video we are looking at the standard normal distribution, and this is for learning intention number 52, and this is part 1. Okay, so in the previous video we looked at the normal distribution. Now we're looking at a more specific case called the standard normal distribution. So I want to explain why we actually bother to look at this particular case, and then we'll go through some examples. So if you remember from the previous video, we met this probability density function called the Gaussian distribution or the normal distribution, and it looked something like this. There's 1 on sigma root 2 pi times e to the power of -1/2 x minus the mean over the standard deviation all squared. And it's really hideous. The area under this curve is 1 and it only spits out positive probabilities, so it's a probability density function, but it's just really hard to calculate with. Especially back in the old days when you didn't have your CAS calculators. So what people did was they said, well, how can we make it easier to calculate with? So what they did was they said, okay, let's just make this sigma value, let's just make it equal 1. So let's let sigma equal 1, and let's let the mean equal 0. So let's set values for each of these. And then that makes it look a bit nicer. So you get this f of x equals 1 on the square root of 2 pi e to the power of -x squared on 2. This is still hideous to calculate with, but it made things easier back in the day, and what people did was they came up with a set of values. So some hardcore mathematicians figured out, okay, here's a table of values you can use to work with this thing, because you just can't, it's just really painful to work with. And you can do this simplification provided you remember that the standard value, so you'll understand more of what this means, but you can do this provided that z equals x minus the mean over sigma. So this is the thing you need to remember. This is very important. That to get a standard score or standard value, you take the x value, you subtract off the mean and divide by the standard deviation. This is the formula you need to use, not these. This is the formula you need to use. Also, the way we denote the standard normal distribution is like this. We say x is normal with a mean of 0 and a variance of 1 squared, or just 1, really. The squared's there just for formality. So this is how we say it's a standard normal distribution. X is normal with a mean of 0 and a variance of 1. This is your standard normal distribution. Why standard? What does this mean? What's this all about? Well, if you imagine, I'll try to give you some analogy. If you imagine you're a bunch of, I don't know, you're a bunch of farmers, and please don't write this down, but you're a bunch of farmers and you all bundle your sacks of flour from your silo in different sizes. So one wheat farmer says, no, my bag's this big, my bag's this big. Another one's like, no, my bag's this big. Now, what you do to compare them is you say, one's the standard, you say this is the standard size. This is 1. This is 1 unit of flour, and then everything else is in relation to that. So if that's 1 unit of flour, you might say that that's 2.1 units of flour. You might say that that's 0.6 units of flour. So you just choose a standard and you relate everything to that. Here you just choose a standard, which is the easiest case, and you relate everything to that. Okay, enough of the hand-wavy explanations. I'll show you what you actually need to do here. So for our first example, we need to calculate the value of the following probabilities correct to 4 decimal places. So I have one probability, and it's within this range. So this is Z. So as soon as you see Z, it means it's a standard normal distribution. So I'm going to draw the standard normal distribution for you. It looks like this, just like all your others, except the mean is 0, and the standard deviation is 1. So it just goes -1, -2, -3, 1, 2, 3. That's it. Just simplifies things. So we're looking for the probability that Z is between -2.02 and 1.59. So we're looking for the area under this curve between here and here. We're looking for this area. Now, how can we find this area? Well, you would have to integrate over this. So what you would actually have to do is integrate from -2.02 to 1.59 across your standard normal distribution, but that's a hideous thing to do. Requires lots of serious maths. So you use your CAS. Your CAS, you don't even need to type this. This is so common that your CAS has an inbuilt function to calculate this. So calculate the value of this probability correct to 4 decimal places, and make sure you're familiar with this function to do this, because we're going to use it a lot. Loading, loading, loading. Okay, calculate. So pop over to menu. This is probability. Go down to your distributions, and we are looking for the normal cumulative distribution function. So we grab this one. Here we are. So what this does, it assumes a lower bound of -infinity. So it assumes it fills all this, but our lower bound here is -2.02. So let's put that in. It's -2.02. Our upper bound is 1.59, and you can see it's already filled in for the standard normal distribution for mu and sigma, so we don't need to worry about that. Let's press OK. There you are. 0.9224 is your answer. Watch out, once correct to 4 decimal places, don't mess up your rounding. It's 0.9224. So we can write that the probability of it being between 2.02 Z 1.59 is 0.9224. That's your answer. And that's the question done. Okay, for this next example, we're going to use this formula here. So we're going to do something called normalize our x. So we have x. X is normally distributed with mu of 50 and sigma 8. Calculate correct to 4 decimal places the probability that it lies between 28 and 65, this continuous random variable. So what you do is you create a z value. So you say, alright, I'm going to normalize this. Write out your formula, z equals x minus mu over sigma, and do your substitutions. So what have we got here? X is normally distributed with a mean of 50 and a standard deviation of 8. Calculate correct to 4 decimal places the probability it lies between these two values. So we have to normalize each value. So I've got 28, which is our x, 28 minus 50 over 8, and that equals, so we get negative 11 on 4. We can use our CAS here. 28 minus 50 divided by 8. Let's get a decimal. Control, enter, negative 2.75. Okay, so we'll call that Z lower if you like. Let's calculate Z upper equals x minus mu on sigma. Our x is 65. Subtract off the mean, divide by the standard deviation. So we get 15 on 8. 15 over 8 gives us 15 over 8. Yes, I want a decimal. Decimal 1.875. So really what this question is asking is find the probability that we're between negative 2.75, whoops, and we changed that to Z, we've normalized it, and 1.875. Now you can use your CAS. Okay, so let's get out, let's go to menu, probability, distributions, and we want the normal cumulative distribution function. This time we're going from negative 2.75 to 1.875. Enter. There we are, 0.9666. 0.9666. That's our answer. Alright, now here we start to have to draw pictures, and we start to have to use the symmetry of the bell curve. The bell curve is symmetrical, so we have to start using this property. So we've been given probabilities, we're told, so we're given a standard normal distribution. There it is. And we're told the probability that Z is less than B is 0.8. So we've been told the probability of, let's say that's B there, the probability that Z is less than B is 0.8. So really it should be around there. So we'll call that B. So the probability of Z being less than B is 0.8. The probability of Z being less than A is 0.25. Remember, this less than or equals thing doesn't matter when it's continuous. So 0.25, so that might be around there. Let's change color. That might be around, there's A, so the probability it's there is 0.25. And it wants us to calculate the probability that it's within this interval. So the reason I guessed B was about there is because 0.8 is the value, so it's got to be about 80% of the area under the curve. Here it needs to be about a quarter of the area under the curve. And we need to figure out this interval, this probability that Z is between A and B. So what we want to find is this area. Well, if we know the green area and we know the blue area, we can find the black area. So the black area is going to be the green area, which is 0.8, minus the blue area, which is 0.25. So the probability of Z falling between that interval is 0.55. Alrighty, last example. Example 4. So we have X is a normal random variable with mean 16 and standard deviation 2. And Z is the standard normal variable. I forgot to get the rest of the example. Find M if the probability, hang on, let me grab this example. So we need to find M if the probability of X being greater than 18 equals the probability that Z is greater than M. So I'm going to go back to my, whoops, there's my videos. Okay, so the question here is, find M if the probability that x is greater than 18 equals the probability that z is greater than m. What's going on here? Well, as soon as you've seen x and a value, and it mentions something about standards, you normalize. You do this. This is normalizing. As soon as you see the word standard and a z, normalize whatever you see around the x's. So let's normalize that 18. So z equals x minus mu on sigma, which equals 18 minus 16 over 2, which is 1. So we can rewrite this problem here as the probability that z is greater than 1 equals the probability that z is greater than m. And something should pop out at you. You should see that, aha, that means m must be 1 for these to be equal. So therefore, this implies that m equals 1. And that's our answer. So you can see it's just getting you to kind of work backwards there. Yeah, you're working backwards. There's another way you could do that. I'll show you another way. Same sort of thing. I'll chop off this. Another way is you could write your formula z equals x minus mu on sigma, and you can say, well, I know that I want to turn m, I want to denormalize, I want to go backwards. So you can sub in m there, and then you can go x minus mu, which is your mean, over sigma, which is 2, because you know m's going to be your standard normal. And then you can sub in your x value right in there. So it's pretty much the same thing. 2 and m equals 1. So that's another way to think about it. Sub in the z part over here, sub in the x part over there. In part 2, we're going to look further at this, and if you have been, thanks for watching.